Hello, thank you for joining. So, welcome to the summer series, and it's great pleasure to see such high attendance today. Typically, it's like a small meeting for maybe 3-4 people, but today's subject could be of interest to broader audience, and therefore, invitation went to larger audience. For the rest of the summer, we will talk to group members for volunteering and presenting on one hand, and on another for sharing, for transferring knowledge on the special subjects that were not part of the class, but the special skills which will be practiced today by Aaron when he will talk about photoluminescence of metal-organic complexes, which is connected to dynamics of photo-excited states. So once again, welcome for joining, and Professor Asurov, nice seeing you.
Professor Kilin, everything fine?
Yeah.
I thought you already started.
Just started. So Aaron, do you have the opportunity to share screen?
I can try real quick.
Okay.
I do not.
Okay, let me. Will you please try now? Okay, and as since we have a broader attendance than usual, please try to make maybe a little verbal introduction of the impact, the motivation, and just broader context of this problem from both applications and methodology. Not too much details, but introduction. Okay, floor is yours.
Am I unmuted?
No, we can see and hear both you and your slides. Yes,
okay.
You are unmuted. Yes.
Okay, so the title of the slide is a little nondescript. So overall, I was jumped into this project halfway through. So essentially what we are looking at is metal-organic complexes and trying to modify functional groups on the complex to change the photophysics, essentially. And the overall goal is to try to get a metal organic structure like this one shown here to emit in the IR range or near IR by changing these side groups of the conjugated ring, which are represented with this dotted line. And it's either capped with hydrogen, unconjugated connection of the rings, or conjugated connections of the rings, which are labeled with A, B, and C. And then there's also changing this R functionalization, which looks at changing going from a little electron donating to electron withdrawing groups, 1 through 5. And I guess initially, most of the computational work on the structure was done doing TD-DFT to look at the photophysics. These calculations were done by Levi Lystrom, and from his calculations, he found two trends essentially. So that's with increasing electron withdrawing group, so going from 1 to 5, there's a consistent redshift, as you can see in the middle panel below by the dotted line. And then with increased structural rigidity, so going from A to C, there's also an increased redshift as a common trend. And so we can see that from the TDDFT calculations, the transition energies are essentially in the range that we are looking for IR emitters, where like 1.5 EV is like 800 nanometers. I believe off the top of my head. So from changing the functionalization groups, we can tune the band gap to the ranges that we want. And so that was essentially the first half of this project that was done by Levi. And then the second component, which I'll be mostly presenting about today, is trying to characterize how efficient all these various complexes are in emitting photoluminescence. And before I get too far, I'll just note that for these calculations that Levi did, there were a total of 15 structures. And for the calculations that I have to do, we essentially narrowed down the amount of structures, which give a qualitative agreement between the different softwares that we use to calculate the photophysics. So for the absorption spectrum, that was all done in Gaussian 16. But to do the dynamics, to simulate photoluminescence, our codes are optimized for VASP software. So we did a check to see which compounds give agreement in terms of trends of going from red to blue. And we found that we narrowed down just looking at the A, B, and C for the 1, 3, and 5 functionalizations. So the most withdrawing, the most donating, and then the middle group, which is the 3. So the in-between groups. And so we narrowed down the structures, and essentially we did our dynamics calculation for these structures, which involves coupling electronic and nuclear degrees of freedom together to describe radiative and non-radiative transitions after a photo excitation. And so before getting too far into the dynamics, I'll just show some orbitals so that we have a feel for the electronic states that we're most concerned about in these complexes. So here I plot the HOMO -1, HOMO, LUMO, and LUMO +1 orbitals for the 9 complexes that we investigate. And essentially the main trend is that for the 1 and 3 functionalizations, so the electron donating and neutral, or more neutral group, they behave, or their orbitals are fairly similar in character. So the HOMO and LUMO are mostly on the conjugated aromatic regions of the molecule. And the LUMO +1 is located on the transition metal for these 1 and 3 columns. But for the most electron withdrawing group, this NO2 group, there's a qualitative change in the ordering. So the HOMO is still relatively localized on the conjugated backbones, but the LUMO orbital starts to get pulled into the withdrawing group more and more. And the most extreme example is this 5C molecule, where the LUMO orbital is mostly resides on the withdrawing group. And yeah, I think that's all I have to say about this slide. And it's just, I'll be referring back to these orbitals later when trying to understand some of the dynamics that I computed. So that's why I'm spending some time looking at these. Then the next slide is just showing, or it just overlays the LUMO orbital, which is the yellow regions, and the HOMO orbital, which is the blue, dark blue regions, just to show that with increasing withdrawing groups, the optical transitions will look more like charge transfer. So you'd expect them to be lower intensity or lower probability of happening, so darker in nature. So that's an understanding of the orbitals. And so next, to do the dynamics, we compute molecular dynamics trajectories for all the compounds. And these are plotted here for the 9 complexes that I'm looking at. The LUMO and HOMO orbitals should be labeled for each of these fluctuation figures to give an idea of like where the band gap is. And there's not a lot interesting just from these by themselves. We can see that the HOMO and LUMO orbitals are well behaved. There's not a lot of state swapping going on, which is good for me because it's less work that I have to do overall. And then the only other noticeable feature is that this LUMO plus 1 band, which is centered on the transition metal, kind of fluctuates fairly a lot, which isn't, overall won't be too important for the figures to look at. But then another thing that I'll mention in passing is that we can see that near the band gap, there's a low density of states. So you can see, like in this HOMO minus 1, HOMO minus 2, there's not a lot of bands. And same with LUMO and LUMO plus 1. But then at higher energies, that's when the states become fairly dense, which will be important for choosing initial conditions for dynamics. Because the HOMO-LUMO energies are like 1 to 1.5 EVs, but to do like a excitation where the bands are most dense, those are fairly high transitions, so you won't see them very much in experiment. So those are the band fluctuations. And then the next slide is essentially the most, the most requested aspects of these calculations, and they are the radiative and non-radiative relaxation rates for each of these compounds, and the resultant photoluminescence quantum yields. So in the top left just shows the schematic for the different functionalizations used for this indium complex. The top right shows the non-radiative recombination rates for the HOMO transition. And then the colored boxes correspond to the different functionalizations. In the bottom left panel is the radiative recombination rates for each of the complexes. And then the bottom right panel is the overall photoluminescence quantum yield, which is just the radiative rate divided by the sums of radiative and non-radiative. And The one trend that kind of sticks out initially is that, at least for the top right panel, for the non-radiative rates, we can see that the 1 and 3 functionalization groups, so the bars surrounded by the green and red, it show a similar trend. I think that's due to like their orbitals being fairly similar in nature. Or we can see that the non-radiative rate shows a minimum for the B functionalization, which is the non-conjugated connection of the ring. So one takeaway seems to be that including a non-conjugated portion to the backbone helps reduce non-radiative recombination, which is what you want for to maximize photoluminescence quantum yield. And then the 5 series, which is the most electron withdrawing, kind of bucks that trend due to their electronic structure being just fairly different. And the other thing I'll note is that for the radiative recombination for each of these molecules, we can see that the electron withdrawing groups have by far the lowest radiative recombination, so in this black box, compared to the red and green boxes. And that's attributed to the increasing charge transfer nature for these transitions. So they're more dark than these 3 and 1 functionalizations, which are more pi to pi star. And then overall, for PL quantum yields, we can see that for the 1 and 3 functionalizations in the red and green boxes, the peaks are with the unconjugated functionalization. And that can be rationalized as that the unsaturated portions help provide stability. It doesn't introduce additional non-radiative effects, so that the quantum yields are maxed with those. I guess before I go on to my next slide, which has more to do with relaxation kinetics, are there any questions on this slide? Just how to interpret the results, or just any general questions?
Questions are encouraged, and if someone is not sure to ask or not to ask, one can also type in the chat line.
I think I asked this question before, just want to be sure. So these calculations are based on the ground state population of states, how to say, you're not really populating your excited states, right? It's kind of a fake population. Your electronic wave function is not affected by the excited state population. Is it true?
Yes, we assume ground states. We do all the dynamics in the ground state, assuming that there's not a large degree of change. Say if we shifted an electron into LUMO and put a hole in the HOMO. So yeah, everything's ground state.
But in general, is it possible, have you ever tried to do the dynamics kind of with these keywords fixing the position of electron in some specific state?
Mm-hmm. Yeah, it is doable. But then, there haven't been any requests to do it for these specific compounds. And I know in a previous meeting you were wondering about PBE versus PB0. I do have results for those for one of the complexes.
Dynamics.
Yeah, for the dynamics. That'll be in a couple slides.
Okay.
Yeah, so this is one of them. Asking a question or no? I guess not. Okay, so this is one aspect of the calculations that I ran. I guess I'll mention one additional thing. So I guess the overall goal for this project is to find bright IR emitters. But the one drawback is that for the reddest photoluminescence that we can get by functionalization, those seem to show the least efficient luminescence out of all these compounds. So that's kind of the drawback, is that we can functionalize to tune the band gap to a favorable position, but due to the changes in the orbitals, it makes them darker in nature. So it's kind of a disappointing aspect. So that's just characterizing the HOMO-LUMO transition. But with excited state dynamics codes that we have, we can also look at the kinetics after photoexcitations above the band gap. And that's what I'll show next. So this slide is just to give an idea of which excitations I'm looking at for the dynamics. So on the left is just one of those fluctuation figures, and on the right is just a bar graph for each of the bands. And essentially the transitions that I look at are two separate ones. So an excitation from this dense set of bands in the valence band to LUMO, and then also from HOMO to the dense bands of states in the conduction band. So essentially what I'm isolating for is that for the HOMO-LUMO transitions, those will give information about the hull cooling kinetics, as the hull goes from HOMO minus X to HOMO, and then the electron cooling dynamics by exciting the electron from HOMO to LUMO plus Y, and letting it cool back down to LUMO. And so this is the first set of calculations trying to visualize the kinetics. So before I go too far, are these figures clear as to what they're showing?
Aaron, probably introduction to these figures is needed because we have broad attendance today.
Yes. Sorry, it's me.
Mm-hmm.
I'm just wondering, okay, the y-axis is a dimensionless energy. Okay, x-axis is time. It basically shows the decay of the holes, or in other words, it's the decay of the excited state. You know, one complex, there is a little bit more difference when the substituents varies, and the decay of the hot hole cooling is slower, slightly slower than the hot hole cooling for the compounds 5, right?
Yeah, so I guess the two trends that I observed throughout, like the two consistent trends, is that the hot hole cooled at least much not much faster, faster than the electron.
Yes,
So the
that's
electrons
right.
are all at like 10
Mm-hmm.
to 100 picosecond lifetimes, where the holes are normally around like between 1 to 10.
Mm-hmm.
And then another trend that I noticed, which would agree with the quantum yield calculations, is that the B compounds, it's not entirely consistent, but these ones tend to show a slightly longer lifetime
Mm-hmm.
than the other ones. And that would make sense because the Bs are supposed to minimize electron phonon interactions. So if
Mm-hmm.
you have a lower intensity electron phonon interaction, you should have longer lifetimes.
Yes.
So those were the two consistent trends that I
Yeah,
observed.
then another trend, that's what I just see is when you look at the 1A, 1B, 1C, it looks like that's the compound with different substituents, but without any connection between the pyrrole and the phenolene. So in that case, the substituents looks like an electron donating group. Let's see, electron donating group, that's a dash line 1A. Oh, another thing is when you look at the decay time, do you really look at the decrease from 1 to almost 0, or you look the half, the time when it decay to half of the maximum?
So it's fit to a single exponential decay, regardless of transition energy. So they all have different transition energies, but just to visualize them, I just normalize
Okay.
by the energy.
Yes, I understand that part. I was just wondering, when you say the cooling time, do you count the time from the 1 decrease from 1 then to the 0, or you count the time when it decay to half of the maximum, decay to 0.5? How do you define the decay time?
So it's a single exponential. So it's decay to 1 over,
1 over E square?
so to 33% of the normal.
Okay, 33 or maybe about 25, 26%. 1 over E square, I think it's about 20, 23, or maybe 18%.
I forget the general rule, but
Yeah, general rule is 1 over E square.
yeah, so generally that's how you can look.
Oh, okay, I see.
Like in the code, it's a little more nuanced, but it's essentially the same. Should be the result.
I see. Yeah, that's right. That's about, yeah, 13.5%.
And
Okay.
so the next slide is essentially all the same data, but instead of comparing the same R functionalization in different side groups, it's just a different look to seeing if you have the same side groups, but then you change the withdrawing or donating groups.
Oh,
Just as,
this one basically you have the same side group, but you just change the connection.
yeah, it's just another way to look at the data
Mm-hmm.
to see if there's any noticeable trends.
Yeah, in this case, the trend is not that obvious. Only, the 5A, once the conjugation, it become more rigid. Also, when it's fully conjugated, then the cooling time looks like it increased a little bit for the 5A.
Mm-hmm.
But for the 5B and 5C, looks like there is not much influence on the hot hole cooling. On the electron cooling, yeah, it has some effect.
Yes, go from A to C.
Mm-hmm.
That seems to be essentially changing the charge transfer character.
Yeah.
Like A is kind of mixed between charge transfer and pi star, whereas
Mm-hmm.
B and C are more fully charge transfer.
Oh, I would see is, as far as I remember, B is has more of the charge transfer. No, the Pi star character is A and C has a little bit more charge transfer, especially C has more charge transfer character. Yeah, you can click that one. Let's take a look.
Yeah, just to look. It's hard to see if they all seem to have like the same amount on the withdrawing group.
Yeah, that's right.
So it's hard to say, but from the PL quantum yields, A definitely had the highest.
Yes, that's right.
5A, B, and C.
I think that one, even last time you recall that we discussed the energy gap law for 5C, the one with electron withdrawing natural group, emission is the most right shifted. So we believe that one was, mainly governed by the energy gap law, which means while it's further right shifted, the non-radiative decay rate increases much more. Therefore, it basically decreases the quantum yield.
Yeah, if there aren't any more comments about these last two slides, the next slide will focus on this 5C decay as obvious bi-exponential.
Yeah, that's right.
Decay kinetics. And just from looking at the orbitals, it's fairly easy to see why. Why the electron is bi-exponential, but the hole is fairly mono or single exponential. So the top half of the slide shows the hole cooling, and the bottom half shows the electron cooling. And there's also a comparison of these calculations with different functionals. So the dotted is PBE, and the solid is PBE 0. And I guess first I'll describe the hot hole cooling. We see comparing methodologies, there's not a drastic change. They're basically identical in their cooling kinetics. And then if you look at the orbitals involved, so the initial state that I chose was HOMO -4, which is this very far one on the right. We can see that all the densities on the conjugated ring, essentially, in some of the groups. And then as it cools to LUMO, basically all the steps involve transferring to other states which are on the ring. So they're close in energy and have fairly high overlap in their orbitals. So it's pretty quick relaxation to the HOMO. Whereas I'll transition to looking at the hot electron cooling on the bottom. We can see that first comparing the functionals is that the PBE gives slightly quicker relaxation than PBE 0, but overall the qualitative trends remain the same, where there's a noticeable bi-exponential. And that can be attributed to the fact that the initial state that I populated was LUMO +4. And then looking at that orbital, it's hybridized between the conjugated ring, and then the transition metal has a little bit of density. So initially, there's a fast cooling, which I call this metal-metal transition, since there's orbital density on the transition metals to this intermediate electronic state. But since now that it's localized on the indium metal, it has a hard time transferring to LUMO and LUMO +1, since those have negligible density. So that's where the second long lifetime comes from.
And so, Aaron, when you talk about the fast decay is from the ligand to the metal, it certainly also supposed to go through the LUMO +3. That one is on the substituent part, right? Does the decay go through from the LUMO +4, then to LUMO +3, then go to LUMO +2?
I didn't check. It's possible to check to see where the populations transfer. But I just assumed that since all the density was on the withdrawing group, that there wasn't.
Yeah.
There's not a lot of pathway. There's not a lot of population going to LUMO +3, but it all kind of bypasses the LUMO +2.
So there is no obligation that it goes step by step, that it goes through all levels. It can really jump through the several levels. And in particular, LUMO +1 and LUMO +3 have very small splitting in energy. But the couplings, if the couplings are very small between them due to the no overlap between the orbitals, so then it can really jump to LUMO +2 without really spending time on LUMO +3.
I see.
Yeah, as long as it goes down in energy, that's like the main requirement. It doesn't have to be in stepwise.
Yeah, and these processes, because it's dynamics, right? So it is how to say, when you calculate your couplings and actually do these dynamics, right? So it's really you average over many events. So it means that it's more like probability. So it doesn't mean that it's not happening at LUMO +3. So just much lower probability to be in LUMO from LUMO 4 to LUMO +3 comparing to LUMO +4 to LUMO +2, right?
I see. So
we're not just tracking single electron with jumps somewhere. You can think that we have a pool of electrons which we average statistically to see in average where they are more probable to go.
Right. I try to understand it also is because LUMO +4 and LUMO +2, they both have significant electron density on the metal, so that probably favors, favors the decay from LUMO +4 directly to LUMO +2. Oh, okay. Yeah, I'm good.
I don't really have any much more to say.
So, but this kind of character you notice only for the 5C case. I know the this by exponential trend is only for 5C electrons, right?
Well, it's the most pronounced, or there's the biggest gap in lifetimes.
But does it mean for the other cases when you have 5A, 5B, or whatever, 1A, 1B, they go more like holes, or what? Or they just have more hybridized orbitals?
Yeah, I would guess they're more hybridized, because if you look at 5B, so the green dotted, you can see that it's not.
Has a little bit,
Yeah, it has a little bit of a tail. So it slows down near the band gap.
Right.
So if you stare at a lot of these for long enough, you can kind of see which ones have a little bit of bi-exponential character to them. But it's mostly for the electrons and the holes, because in the conduction band, it has that orbital centered on the metal. So that can kind of act as a inhibitor to cooling.
Yeah, I can see 5B definitely it has the by exponential decay for the electrons.
But A doesn't. A looks like it's always.
Yeah, it does not look like unless I think when it's close to the maybe 80s or 90s. I'm not sure whether it has a small bumper there because it overlaps with 3A.
Yeah, I think there's a little bit, like right here. It doesn't.
Oh.
It has a slightly different curvature.
I think it's even longer, close to 100 picoseconds there, even almost, go down. Yeah, 5B is clear. I think it does have the, yes. So in that case, maybe you can also do a similar analysis for 5B, just like what you did for 5C.
I would probably suggest do it for 5A instead, because for 5B we probably will see the same picture, and it may be just the splitting in electronic levels a little bit different, not as big as for 5C, and that's why it goes faster. But I think 5A is probably lacking this feature, so probably it's more interesting to look on a limiting case 5A.
Oh, the thing is 5B and 5C, the nature of the orbitals are different. B and A, the orbital nature, and at least the frontier molecular orbitals we just saw, those are quite similar.
Oh, can we take a look on
That's page 8, right? Yes, that's 8. Yeah, those just involve homo LUMO, homo plus 1, homo minus 1 and LUMO plus 1. And here we are dealing with, plus 2, plus 3, plus 4. So whether those orbitals are still similar. From the orbitals provided on this slide, it looks like 1 and 3, they are pretty much similar.
But looks like then what I'm see. Can you return back to your previous slide? I mean the one which we just looked recently.
8. Slide 8.
No, with orbitals.
Or the orbital?
Oh, yeah, that's slide 8.
Yeah, this one. I mean, it takes time too. Yeah, so it looks like in the case of 1 and 3, right? So we have LUMO plus 1 being d orbital. And I guess this d orbital is happening to appear as LUMO plus 3, LUMO plus 4, I think. Yeah, LUMO.
It was LUMO plus 2.
LUMO plus 2. And it's happening as LUMO plus 2 for the complex 5, right?
Yes,
for
that's right.
Complex 5C, which we saw.
Right.
So, but I think through the dynamics, it looks like your LUMO plus 1 still stays as d orbital, right? But we don't see this slowing of the curve in the case of 1 and 3. Like there's no big exponential changes in the case of 1C and 3C. Am I right?
Yes, that's right.
Yeah.
Or even 3A, 3C, because they're all showing A, B, and C, 1 and 3. They all show LUMO plus 1, mainly just pure d orbital state, right? So then I'm just curious, like if I think what you explain is very, very reasonable. The only then question would be, you still have these states in case of 1 and 3, but they happen as LUMO plus 1 rather than LUMO plus 2, means they happen kind of close to the age of the when the relaxation is finished. Is it the reason why we don't really see this this bump, this additional B exponential trend? And also, is it the reason why it's really, you see that electrons in all cases are slow comparing to the holes? Because of the presence of this d orbital. But in case of 5, this d orbital is happening higher. I mean, you how say, higher in energy, right? So earlier in time. So that's why it's kind of have to jump there, live there for a while, and then returns back to its to the luma, to its lowest possible state. And in case of 1 and 3, because it's luma plus 1 is probably already very close to luma, and it's kind of, we don't really see this these bumps in your exponential curves.
Yeah,
Yeah.
I think that makes sense. That's also what I suspect, and that's what I think is just look at 5B is basically you just look at the luma plus 1, 2, 3, 4 to see the nature of those molecular orbitals. Then what Splana just explained. I think it definitely it makes sense. That's our assumption, but if you really actually look at those orbitals, it just confirm it.
Right, and I can also look like in the dynamics code that we use, we can track the trajectory of the populations, and so that would be a natural thing to look at to see if if the electron like bypasses this d states to the LUMO, because you wouldn't see an increase in population in time if it bypassed it.
Right.
I can do that for.
Yeah, it actually can be also that it might really jump through to the luma directly because of the stronger couplings between, let's say, luma plus 3 and luma rather than luma plus 3 and luma plus 1. It's also possible.
Right.
And luma plus 1. So it's kind of also can jump in the same way as we explained that luma plus 3 is probably not very much populated during the dynamics because it's so much, because the couplings will be very small because it's so much localized on the substituting group, while the previous state is completely localized over the ring and the d orbital.
So yeah, just from looking at like the fluctuation figures, so we can see it for the electron. If it's in LUMO plus 3 or 4, like it either transfers to the metal and has a long lifetime to LUMO, or either, since there's a big energy gap, it'll have a longer lifetime too. So it could be either one of those. Yeah, I can put that on my list of to-do figures to accompany the slides.
It looks like it's it definitely shows the difference, so it would be interesting to see a little bit more details on it.
Yeah, that's right.
And so then, yeah, the last new data that I'll show is just the test of functional. So we've already seen the left-hand slide of these, comparing the cooling kinetics with PB and PB0. So on the right is a table that compares oscillator strength, the transition energies, and the resultant rate constants for radiative, non-radiative, and quantum yield.
Ooh,
and so
we have twice difference actually, at least twice difference.
yes, I was kind of surprised at that at first, because since the oscillator strengths are the same, I wasn't expecting a big change in the yield.
So probably the splitting in states, yeah, because PB1, PB0 will provide you stronger, probably bigger splitting comparing to PBE between different states.
Yeah, I guess it's kind of like that, but I guess for the rate constants,
it also might change the orbital localization, right? Oh, I don't know. Did you check? They are similar in the nature of orbitals.
yeah, the orbitals looked similar.
We expect that pure GGA functionals have a tendency over delocalize the orbital. And if it's over delocalized, you expect that the couplings should be stronger and then the rate should be quicker. But it looks like it's completely opposite, right? Because you have bigger rate for the hybrid functional.
Mm-hmm. Yeah, I think, well, I know that is attributed to the increase in the band gap. So PB0 or PBE underestimates the band gap, or PBE0 gets it more qualitatively correct with experiment. And in the rate constant calculation that I use, there's one input for the oscillator strengths, but there's also, it depends on the transition energy. And so since there's more than a 2 times increase,
Oh, squared, yeah. So you
yeah,
have,
then it gets squared. So then, yeah, that's where the big bump.
yeah. Then again, would be maybe making sense, like when you come. So this is the dynamics, right?
Mm-hmm. And so, yeah, the energies and the oscillator strengths are averaged.
You have the ground state calculations with PBE0, right? I mean, before dynamics, just at the ground state. I think you were showing your data for the spectra, or for the gaps and spectra in the beginning.
Yeah.
I just think it would be good information to add for the orbit, showing orbitals with PBE0 functional. Maybe it also makes sense to create a similar table with PBE1, I mean, with a hybrid functional, right? PBE0. Just to show that functional doesn't change. If the functional doesn't change, if we don't see by eye big difference in localization, delocalization properties of these orbitals, then during dynamics also probably it's a very low chance that something will be significantly changed, right? And then it's really more to the issue with energy splitting rather than with the change of the orbital localization, which will lead to the different couplings. I mean, which also will contribute to the different couplings.
Mm-hmm. Yeah. We didn't talk about it yet, but there is a small difference in the couplings. It's like a factor of 2 increase from PBE to PB0.
But this is not couplings, this is already rates, right?
Yeah, those are rates.
Yeah, those are converted to rates.
Which means you already have both contributions to the, both couplings and the energy terms are there, right?
Yes. Like not in any formula that I use. So it's, we basically just compute correlation functions of the couplings to get rates. So energy isn't like manually put in, but it's should be accounted for in the orbitals.
Oh, actually, I'm confused here. For your radiative couplings, I'm still don't understand. Then I don't understand your formula here.
Let me contribute to the discussion. So the protocol to get the quantum yield, which is an objective observable, is the ratio of radiative and non-radiative. And through this approach, we are not bound to absolute values of this rates. So one should look for the column 4 and 5 in PB and PB0, different functionals, and look how this radiative and non-radiative compare to each other.
No, my confusion with the formulas which you show in here, my confusion, your formula doesn't include any non-radiative couplings.
For the
I'm now
K
confused. It depends on the oscillator strength, it depends on the energy splitting, that's it?
for the radiative.
Yes.
Then the non-radiative. So the couplings are these V things.
But for your radiative rate, non-radiative couplings are not contributing?
Radiative? No.
The radiative couplings are just Einstein coefficients. Coefficient of spontaneous emission, which does not depend on the coupling to phonons. It's only interaction between electronic degrees of freedom and modes of quantized electromagnetic field. So it's reasonable.
But you can expect that, for example, if you have a if you have a transition between two states, right? Let's say, I don't know, luma plus 5 and luma plus 4. Both of these have a strong oscillator strengths. Both of them have whatever, like each of these terms, the green and red terms which contributes are good and high enough, right? But if your couplings between HOMO 5 and HOMO 4, when you do dynamics, if this coupling is very, very small, is very, very insignificant, it means it will never really go to the HOMO 4.
Okay, you are correct in the following, that if the emission is contributed by multiple channels, then instead of single number for radiative and single number for non-radiative, one needs a matrix for all radiative and matrix for all non-radiative. And then it will be not as easy to put it into a table and analyze by human eye. Then one needs some additional procedures, which Aaron, I hope, will show in like 3 or 4 slides.
Okay, I got it. So your radiative rates really contribute. So you already assume that the radiative rate contributes only from HOMO luma. Like you cannot really have emission from luma plus 4 to HOMO or luma plus 1 to HOMO. Although in reality it's possible, right? I mean, in real samples, you not necessarily expect that emission, spontaneous emission, will really happen exactly from the low state.
But mostly.
Yeah. Well, so in this slide, Aaron is showing a limiting case when emission happens only between HOMO and LUMO.
Okay.
And after this limiting case, he's going to explore further if the multiple channels contribute.
Okay, so I got it, because I saw that you really include more than just a single state. Let's say if you go, like you said, like hot relaxation, lower relaxation, which I thought you also contribute to the radiative rate, or kind of check-in that you might really go from luma plus 1 through the radiative channel, because if it's having a strong oscillator strength between these transitions, right, then why not?
Yeah, so I guess.
But you not really consider these processes. Okay, good. So honestly, I think it's really, even this contribution can be probably neglected, because even if it exists, it's probably a minor. Not a minor contribution. So it would be just
transient.
Some correction, but not really the governing term.
Okay, then my question is regarding this comparison, PBE versus PBE0. What is the conclusion? Which functional is more reliable, PBE?
I guess in terms of accuracy, it's like you would assume PBE0 is more well suited. So I guess, yeah, this was the next question I was going to ask, whether, because since there's not a drastic change in the oscillator strengths and the non-radiative recombination rates, if we want like slightly improved quantum yield numbers, should we substitute the TD-DFT transition energies in this formula, or stick with what I've been using?
So I think all this new data, where probably you really put your effort on this, getting this new data and comparison between functionals, mainly because of the previous discussion, right? And I think it was generated by, I think, or maybe Levi, don't remember who was the initiator, because there was starting the discussion saying that, wait a minute, when you look on the spectra of PBE, right? So like we have, because GGA functional underestimates the band gaps and the overall splitting in energy. So we have kind of a different energy for one functional and much bigger energy for the other functional. And then the question was, although qualitatively, if we compare in between the trends, everything looks very similar, but the absolute value might be different because, yeah, exactly, because this energy, transition energy contributes like square in these formulas.
Mm-hmm.
So, and yeah, and it's kind of your data now completely shows this this point that although qualitatively nothing really is changing, it means like it looks like oscillator strength the same, which showing that orbitals not really very much affected, like with the functionals, they probably have pretty much the same nature. Again, the trends between different molecules probably also will be not affected, but the absolute value of the rates are affected. We have a difference in twice quicker, or even how many, more than twice actually, depends. Yeah, if you look on a quantum yield, it's about twice bigger, right?
Mm-hmm.
For rates, it's even for non-radiative rate, it's also twice. For radiative, it's even bigger contribution. So so now we know for sure it's really because of this underestimated energy splitting in the GJ functional. Since PBE zero is more accurate in splitting of energies with respect to experimental samples, so it looks like PBE zero is expected to be more trustable data now. If you really want to look on the values of the quantum yield, if we just want to compare in between the series, let's say, just to make a conclusion, who is faster, C or B, or whatever, 1A or 5A, or yeah. So then the story about functionals are not so much important, because how much one is faster comparing to another, I think it will be pretty much the same predictions for both functionals. But if you really need the value to be compared with experimental values for the quantum yield, then I think we expect that PBE zero will be smaller rather than experimental one, because of this underestimated energies.
So even PBE1 is the photoluminescence quantum yield is higher than the PBE1, than the PBE, then you still assume this 0.59 is still will be lower than the experimental value. Am I right? That actually, from the calculated predicted emission energy, I think at the beginning, Aaron mentioned it's around 800 nanometer with 0.59 quantum yield. That's huge, huge. I kind of suspect even 33% is higher, for emission occurs on 800 nanometer. Then 59 is really, I would think is, in order to compare which one is more reliable, I mean, for the functional, it's better to compare with the experimental data, which we do not have. So
let me contribute to discussion. So it is, with all these methods, it is very dangerous to expect literal one-to-one agreement with experiment. There are always so many approximations. And if something goes close to experiment on the quantitative range, it's there is a chance that it's just a good coincidence. And just to be on the safe side and speak about these effects in a like reasonable way, so that reviewers and community will not come after us, it's important to mention these approximations. And one of the approximations made here is that all ions are point charges. So the Frank quantum factors are assumed 1 for any transition, while in reality there is a nuclear reorganization, there are quantized nuclear motion, and transitions will be slowed down, especially the non-radiative, and this will change these numbers towards the lower values. So this probably these numbers of this very high quantum yield are like upper limit. But if one would take into account all other mechanisms, it will be smaller. But these corrections will be too expensive to perform.
Yeah, I think the main problem with the comparison, direct comparison, that this is vacuum calculations. We don't have solvent, and if we have experimental data in a solvent, right? So for solvent reorganization and also some loss of the interactions with the solvent and so on, of course, will be another additional channel for the activating or deactivating vibrational modes, and overall will be affecting the quantum field as well, right? We know that changing the solvent, your quantum field will be also changed, right?
Yeah, especially if it's a charge transfer emitting states, then the stronger, more polar solvent will drastically decrease the emission quantum yield.
Right. So we completely out of these processes here. So it's already showing that we cannot directly compare to experiment. So it's one thing which is very easy, plus all other small corrections which Dmitry was saying, that of course we have kind of more idealized case comparing to the experimental data, which again make this percentage to increase to be more ideal rather than in reality. I just have, yeah, so I think Levi was reminding that we have data for 3A from experiment. Quantum field was showing 75% in a solution. And I don't remember, was it a polar solvent there? Pretty polar solvent, I don't remember which one. Maybe Levi remembers, maybe he can write. But
no, what is the IDK?
ID what?
IDK, he just put in the chat, IDK. I do not think we ever use abbreviation for that one.
It's short for I don't know.
No, I do not think that's a common abbreviation for any solvent. Or DMF?
No. It's abbreviation for I don't know.
Oh, I see.
But it was deceptive. I also thought that IDK is some specific solvent.
I see. Okay, he just said I do not know. Yeah, but one thing is 3A, the emission actually energy should be much higher than the emission energy of 5C. So for 3A, it has, I assume, Levi, do you recall for 3A experimental emission wavelengths, is that 500, between 500-600 nanometer?
639, I think, nanometers.
How many nanometer?
639.
639.
Mm-hmm.
Okay, yeah, but for this 5C, it probably will move to around 800 nanometers. Then I think the decrease will be much more significant. Just yeah, as I said, I think even
we again. So my question to Erin: why you didn't use 3A, which we have experimental data for comparison different functionals? And last time,
interested in that.
Just a second. Last time, I mean, our data when we comparing these quantum fields, right, with PBE functional. So your data were showing pretty good. It was very close to 75 or something like this %, right, with your calculations. If I just take this twice, it cannot be twice more because then it will be more than 100%.
It's a ratio, so it won't be above. Well, I guess, let's see here. No, it'll never be above 100 because it's the radiative divided by radiative plus non-radiative. So it could be like 98.9 or something, but it won't, well, assuming that the calculations are healthy, it won't be above 100.
No, I'm not 100% sure that it's really will be like that, because don't forget, so we have contribution, yes, energy will be higher, which means this red term in the radiative will be bigger, right, contribution. However, when we calculate the rates in the non-radiative processes, so the non-adiabatic couplings, they also depend on the splitting between energies, and they go with a reverse order. So the bigger the splitting, the slower the couplings, the smaller the couplings. So that's why there will be two contributions which go completely in the opposite direction just due to this change in the energy. So I don't know, like you really need to calculate your PBE1 and see how much your rate will increase for the 3A complex. Because not necessarily that it will be such a huge increase there.
Yeah, that's right.
Because it also contributes to the non-radiative couplings, and it might be much more significant change there rather than in 5C. Because I think couplings in 5C are the smallest. Non-radiative couplings, according to your previous calculations, right? Go to the slide with your comparison of couplings and quantum yields. I mean, the radiative rates and rates and the quantum yield between different molecules. Yeah, this one, 11. Yeah, so non-radiative couplings are the smallest for 5. And they're much bigger for 3A. Well, maybe not much, but they're bigger for 3A. So
for homolumo.
yeah, for PBE0, it probably will be even bigger for non-radiatives rates. So it's a good question. We probably will get bigger numbers than 75, but I doubt that it will be 95 or something like that.
Yeah, so I guess my feeling is that like the numbers will obviously change, but if you assume that oscillator strengths don't change very drastically and the non-radiative recombination rates don't change dramatically, the most dominant term is going to be the change in the band gap, which is I would assume to be the same in pretty much all the molecules or all the complexes. So my gut feeling is that like the overall trend will hold, but we'll just have different increased quantum yields, and then radiative rates will probably increase a little bit too. I guess that's just my gut feeling anyway.
Yeah, I think yeah, you using 3A, which has experimental data, it will be a better comparison. Okay, Levi is keeping changing the number. So okay, it says in chloroform the quantum yield is 19%, and in toluene methanol. Are you sure toluene methanol those are room temperature or that's a low temperature? Okay, I'll try to look at the paper.
In this paper, they do everything in normal temperatures, in the room temperature. I don't think that they have any data on the low temperatures.
Okay, let me see. Yeah, that's right.
Well, yeah, in any case, I don't think we should expect exact agreement with experiment, right? Because we know that we don't have any solvent in these calculations, first of all, which already we know the quantum yield is very sensitive to the solvent. And plus other small things which we not include, like our quantum yield will be always higher and more idealized. So I would put another question to decide: should we really force Erin to calculate the quantum yields with PBE0 functional for 3A?
I think so. I would like to, take a look because right now the PBE045C is with 0.59. That one I do not think that one is not reasonable at all.
I guess I would say it's if we did PBE, I would assume that it would only increase, so it would get like less accurate compared to experiment.
Increase, but the question is for how much?
Hmm.
Would it be, because again, if we just thinking should it be twice increase? Of course not, right? So then does it just go from whatever your was prediction? I don't see the value here. Or should I be able to see it?
So it's
We're talking about 3A, right? So it was 70 something. Oh, your prediction was 75, right? Already for the 3A, yeah. So which was higher than 67, but not very far away. So then, yeah, the question is with PB 0, are you really getting something around 90?
well, I guess something that I could check really quick is if I just change the transition energy to the PBE 0 value, like that would give a rough estimate of how much it will change.
You can change this energy only for the radiative rate, right?
Right, because I directly have to plug that into the equation.
Yeah, for radiative rate, it will be very easy. I mean, like it will be not really average. You can take just these values for the ground state calculations. But for the couplings also will be, non-adiabatic couplings also will be affected by this change in energy, which you cannot really put as constant or as something. I think you really need to run the dynamics for that. And they go in the opposite way, right? So with increase in energy, the non-radiative couplings should be reduced. And again, it's more complicated than this because they're not linear or whatever. It's more complicated correlations between the energy and the couplings. So Dmitry, what do you think?
The assessment of the quantum yield is quite quick thing, so it shouldn't be a problem.
But the problem is to get the non-radiative couplings.
For non-radiative couplings, I think it's I don't mind, but we can come into deadly spiral when we want more and more data, and it is more and more difficult to analyze it. So maybe it's better to focus on smaller amount of data and make all logical connections completed, and then go to the next stage. Because Aaron is defending thesis and finishing soon, and it's better to have a small piece completed rather than something postponed for the far future.
Aaron, can you return back to this comparison between PBE0 and PBE for the couplings and quantum yields for 5C? Yeah. So non-radiative couplings are also different twice. I'm really suspicious about these values for the non-radiative. Well, can you explain why we have increase in the non-radiative couplings with switching the functional? What exactly is the contribution for the radiative ones? It's very clear what is going on. But what about non-radiative couplings? What is the reason to have PBE0 giving non-radiative couplings twice higher comparing to the not couplings, non-radiative rates, which of course completely proportional to the couplings? What is the reason behind this increase?
It's tough. Well, just from the calculations I've done, it's tough to narrow it down whether it's not absolute noise, whether there's some noise due to the trajectory not being long enough, or if it's the underestimation of the energy splittings. But I know there's a paper by Alexei Akimov, I think his last name is, and he published a paper about comparing coupling rates between PB and PB0 functional. He found, well, it's different systems, but it was a general trend that he found is that the PB or the hybrid functionals increased the radiative or increased their rates by like a factor between 2 or 5 for the systems he looked at. And he just attributed it to smaller energy gaps.
Are you sure it increases or decreases the rates? Yeah, I remember. So it was showing this this difference, and the difference was significant. You're right.
I thought it was increased because if it's.
I had a feeling that it was decreased actually rather than increased.
Are you talking about the radiative or non-radiative?
No, it just was a completely theoretical paper comparing the non-adiabatic couplings.
Okay.
His equations for equations which Erin is using, non-adiabatic couplings. This is V and NaC at the top. So this is a couplings which contribute to the non-radiative rate. So he will in these theoretical papers, they're not really showing the non-radiative rates. They just talk about the change in the non-adiabatic couplings when we switch the functionals. Yeah. Okay, yeah. So I remember the paper which you're talking about. It's a good reference. Yes, I will take a close look. Yeah. So with this one, we probably especially if our results are very consistent with his findings. I think they were doing it for silicon quantum dot, right? System, the non-radiative dynamics in phonon-mediated dynamics in the silicon quantum dots. Yeah, so if we will be consistent with it, I think we can just refer to this paper and then probably go to the discussion in general that although it's increasing the value, the overall trends, who is faster, who is slow, is really pretty much the same for any of these functionals.
Okay, when you make that statement, it has to be you really really do the work. If that work is not done, then you cannot make that statement. Oh, that the thing is, what's the value or meaning really compare the PBE and the PBE0. I understand from Sumana's explanation is because initially when we look at the UV spectrum, the trend using the different functionals, they are the same. However, it's just the absolute value is not right. And I think PBE is underestimate or underestimate the transition energy. PBE0 is more accurate for predict the absorption. Transition energy. But whether that means it's more accurate in predict the emission quantum yield, from my viewpoint, I do not think so. I just do not think it's possible for for an emission occurs at 800 nanometer. Even I understand the calculated value is different from the theory. From experimental value, but with the emission occurs at 800 nanometer and with the quantum yield of 59%, that's huge. Okay, since I have to leave until 6 and I need some time to prepare for my tomorrow's panel review, so can we just go through the slides to see anything important? I haven't seen before then. Maybe I leave it to you guys to continue discussion.
Yeah, there's not a lot more new. The only additional new thing, so we've seen this slide before, trying to approximate line widths. I won't spend time on that. And so essentially the only other additional thing to show is the photoluminescence during the trajectory. So, how to parse this? So the top half of the slide shows the hot hole cooling. So we've already seen everything in the green figures we've seen before. So this blue decay is the same decay I showed in those slide 13 and 14, just in a different way. But then along this trajectory, the blue figures show time-resolved photoluminescence or transient signals before decaying to the band gap. So the way to interpret this is that there's the initial excitation. So for this top middle blue panel, there's a short lifetime where it has a small intensity, but then it cools to the band gap where this bright blue streak is. And so this is the main photoluminescence from the compound. And then these lower energy features are intra-band luminescence. So instead of emitting a phonon, it emits a photon to release low energy transitions. But then those all go away once it cools to the band gap. And then to the right just shows the integrated emission along the trajectory. So we can see that the HOMO-LUMO photoluminescence dominates the spectrum. So it's not
yeah,
I guess,
you just mentioned something at the bottom. Those are pretty bright. So you just said for that, I mean, decay is also photoluminescence.
so it's so
Bottom left.
Yeah. So the bright color indicates intensity. So it's a very bright, so it's an intense transition.
Okay.
But it has a very short lifetime. So this is a long scale. So this is like 10 femtoseconds to 100 femtoseconds.
Okay, so is that, I mean, transition, that rapid transition, is that radiative or non-radiative?
So it's radiative. So it's like IR spectra.
Oh, okay.
So very IR. So like.
So there is a potential, or there is a prediction of IR emission, but which happens at earlier stage, like femtosecond, 10 femtosecond range. But in the time integrated observations, it will be not seen because it is very small fraction of time.
I see.
So, or it will be like accounted as a noise. So it will not contribute to overall effects. And if someone is really needing it, one needs femtosecond resolution equipment if there is any interest in these effects. But on the global, on the long time scale, it's will be so much smaller compared to main signal that it is okay to skip it. And this effect that Aaron is showing and that is under discussion now, it will contribute more significantly for the systems with very, very sparse spectra, like atomic species, or it was previously seen to contribute to observable part of the spectrum in lanthanides, where there is a placed in the glass matrix with very sparse subgaps. But in this system, it is a negligible effect.
So when you see very near, I mean, infrared, are we talking about, 10 micrometer? Not micrometer. Let me see. If it's 1,000 nanometer, it should be 1 micrometer.
It's electron volts, right? So
yeah, so this is like 0.1, 0.2 eV. So whatever.
Oh, okay.
And it will be grossly interfered by the vibrational transitions. So if one wants to look on it without cooling system to 0 Kelvin, probably this yellow stripe will be still below the intensity of vibrational transition, more standard infrared spectroscopy.
I see. That will be, yeah, if it's 0.1 electron volts, that will be about 12.4 micrometer. So, okay. Then what is the bottom of those two figures?
The bottom two?
Yes. or bottom 3?
Oh, so the top half.
Yeah.
So it reflects a photo excitation where it's like it results in a hot hole only. So it's
Oh.
an excitation from like HOMO -3 to LUMO.
Mm-hmm.
Whereas this bottom half is an excitation from HOMO to LUMO +2.
Oh, okay.
So it's just two different trajectories.
I see.
And we can see that the overall PL spectrum is basically the same, regardless of which path it follows.
I see. Yeah, that was a question I recall from last time. We were asking which wavelengths did you, when you do the calculation, which was the excitation wavelengths. And the last time I recall it was 300 nanometer something. Then we kind of argued, said yes, since the lowest, electronic transition was about 600 nanometer, why not excite at 600 nanometer? So
Right.
this is basically try to answer that question. It said it does not matter where the initial stage it was excited and the final emission should be the same, right?
Mm-hmm.
Oh, okay.
Yeah, and these transition energies are comparable. So like, you could do an experiment. Like this one's 2.3 EV.
Mm-hmm.
That's a little high. But then this top panel corresponds to like a 2.2 EV transition.
I see.
So
yeah. So can you move to the next slide?
Yeah, so I guess they're all basically the same and there's not a lot of change. So this is for the 1A complex. This is for 1B.
Erin, is it true that your oscillator strength for your emission is not affected? I mean, the brightness, the intensity is not affected where you go hot hole relaxation or hot electron relaxation. Am I right? Looking on your very last panel on the right, it's kind of the same intensity.
Mm-hmm.
Yeah. I mean,
all right, so it's
expected to be not affected if you really have HOMO-LUMO transition mainly, right?
Yeah, so the color bar is individual for each figure. So it's not normalized to like the most intense of all the transitions. It's just the ones that occur. So in this top middle panel, we can see that like it followed this trajectory where it had a very intense low energy transition, but in a different trajectory, it bypasses that. So it's not included in the scale. That makes sense. So it's the brightness scheme can be deceiving, but it's all the same transition or oscillator strengths remain the same.
Well, because if I look on the very last panel, right, then the height of this peak is a little bit, looks, again, it's hard to say, but it looks like it's a little bit higher for the top rather than for the bottom.
Mm-hmm. And that can happen because there can be, like one path can be slower to relaxing to the band gap than another. So that can give slight deviations in the total intensity.
But it's really insignificant.
Yeah, but it's dominated. But yeah, the HOMO-LUMO lifetime dominates everything. So it's even if there's like 1 to 10 picosecond changes in the cooling, like the 100 to 500 picosecond lifetime outweighs that. And yeah, so this is the 1B compound, the 1C.
Oh.
The bottom half is a little bit of an outlier.
Oh, this is because of this big exponential curve. Probably that's why you have two peaks in emission.
No, the by exponential is for 5c, not for 1c.
Ah, right. Okay.
Then, yeah, how do you explain this?
So I believe this is an artifact of the current version of the code that I'm using. So it's, how do I describe it?
Could it be if it is not an artifact, can it be a consequence of the metastable state that where the electron is at 1.5, like Luma plus 1 is metastable? Yes.
Mm-hmm. So I think that's correct, but there's an approximation in the way we compute the non-radiative lifetime. So in all these figures, you can see that the blue and yellow lines eventually fade away. And so that's
okay.
So that's the non-radiative lifetime. And ideally,
so I think we can think about this way. Really, so actually this intermediate state, right, which we see as a bright first bright peak in the energy below 1 electron volts, like I don't know what is it, 0.9 or something like this, right? So it's kind of goes from this intermediate state. However, if it goes through the radiative, if it goes through the shining the light, right, through the radiative rate, then I think the time should be something around nanoseconds. But the time to go from this intermediate state, Luma plus whatever, plus 2 or whatever it is, Luma plus 1, right, go to the Luma happens in probably less than picosecond rate. So that's why even if it's technically can be emitting state, it just doesn't have enough time to emit, because it actually goes down to Luma much quicker rather than emitting through the light.
Yes, but in that case, you'd expect the
because this one was showing the oscillator strengths corresponding to this specific states, right?
Mm-hmm.
These bright lines.
Yeah,
they're not really showing the time. Oh, actually, we can estimate the time. I don't know. Can we estimate the lifetime of this intermediate transition?
Yeah. So 0 on the scale is 1 picosecond. So it's like 10 picoseconds.
And then for the next one, which is 1 something, 1.2, it would be what?
So that's,
yeah, that will be tens of picoseconds.
Mm-hmm.
Because 2 will be 100, and if from the 1 is about 10 picoseconds, 10 to 100.
Mm-hmm. Yeah, so it seems like overall they have a similar lifetime.
Also, the strange thing is, I can see the bottom one is the that one is pretty bright. The next one is not that bright. Why it still shows a similar intensity?
Let me contribute, and Aaron can continue. So the x-axis is logarithmic scale instead of linear.
Right.
Therefore, the integration, when just mechanically one performs time integration to convert this bright lines into time integrated spectra, the time increment in procedure of integration is also non-constant. It changes as we go further to higher time. The delta t becomes bigger and bigger. So the events that happen later, and even if they do not appear too much bright for us visually, they will contribute more. So it is not an artifact, it is objective consequence of the log scale. So if it is from 10 picoseconds to 100 picoseconds, it's at least 10 times longer than from 0 to 10 picoseconds.
Mm-hmm.
So even not bright transition will contribute equally.
I see. So this is a question need to be answered, right? Because why it shows the kind of by not really by exponential decay, it's dual emission.
I would not call it dual emission because again, it's not this intensity is not really the real intensity what you will see in the spectra, right? Because again, we not scale it with respect to the non-radiative process. In other words, how quickly the population of this Luma +1 state, how quickly it's losing its population, because this population jump into the Luma, right? And again, if it's losing this population quicker than the radiative time, we will not see this emitting state, despite its intensive character or optical character.
Mm-hmm.
So this effect that we are focusing at right now, that looks a little strange, the bright yellow stripe at 0.7 electron volts. So such effects would be objectively measured on experiment for systems where subgaps are bigger than the primary gap. So if energy offset between like Luma and Luma +1 is bigger than HOMO-LUMA gap, then such transitions would be measured on experiment and play major role.
It's still possible. It's always an overplay of, if the radiative decay, for example, from S2 to S0 is much faster than the non-radiative decay from S2 to S1, then it will directly emit from S2 to S0.
Yeah, I agree. But this is not S1 and S2 states. This is my understanding that this is intra-band transitions. It's not from.
Yes, I would say it is from S2 to S1.
Right.
It's emission from the excited state. No. Or you can say absorption from excited state or emission from the excited state.
From excited to excited.
Yes. But again, I think how we can kind of comparing. If you look on this, the first panel on the left, the green one, right? So at the same moment of time, let's say, because it's logarithmic scale, I really hate to, I really have a problem to interpret it. But let's say we take 1 on a logarithmic scale. So by the log of 1 picosecond, we populate this intermediate state because you almost have big yellow spot there. So it means this state for sure is populated. But at the same time, you have some population of the low state, right? It's not as strong, it's not as yellow, but it's not zero. At the same time, in other words, you kind of populating both this state Luma +1, you also have a population Luma just Luma. And then like in a moment 1.5, you losing the population on this intermediate state, and you increasing the population of the next state. So technically, we just need to take this change in the 1 minus 1.5, log of 1 minus log of 1.5, right? And this probably will give you the lifetime of this intermediate state. Because if we just take log of 1, this would be just the time when this state is populated. So you excite somewhere high, and in 1 picosecond, or whatever it was, a little bit more, 10 picosecond, you populate the state, right? But it doesn't give you exactly the lifetime of this state. To get the lifetime, you need really to subtract, let's say half of population this state versus half a population the other state.
Yeah, that's possible to do.
Because after log 1, we have nothing on the higher states, right? If you take at around 1, maybe 1.2, if you take log 1.2, put it in a picosecond, right? The higher states are completely empty. We have green color there at that moment. So then you can populate the low state after 1 point something, only taking the population of the luma plus 1, right? So which means you really, even if it wants to radiate, it kind of doesn't have enough time because it's depopulated much faster than the rate which you can get if you take the Einstein formula and calculate this rate, right? So it would be longer comparing to the depopulation rate through the phonon interactions, or you can call it non-radiative rate. So I would interpret it this way. This picture with 2 peaks showing only radiative pathway. It doesn't really include non-radiative contribution here. Am I right?
It does include non-radiative. I guess the populations change non-radiatively. And then the total excited state decays non-radiatively. So that we can, because if I did not include like the non-radiative portion, like this main peak here would just keep growing intensely no matter what, because its lifetime would be artificially wrong. So the intensity of the peaks do have some sort of relation to the non-radiative.
Yeah, then I don't know. Then my explanation is wrong. Then it's really strange because you then expect really that you will have dual emission for this species.
Yeah, I think, just from looking at it the past couple of minutes, I think this bright band that I circled or outlined with the red box, that seems to match up with this lifetime in the initial excited state, and it must be emitting so this bright feature I'm interpreting as a LUMO +2 to LUMO.
Or maybe LUMO +2 to LUMO +1, because it is less than 1 electron volt.
Right.
LUMO +1 to LUMO.
So, yeah, this arrow is too long. You need to make it twice shorter, yes.
Not this one.
Yeah, this one, because it starts immediately at 0.
No, your energy for the first peak is something around 0.8 or 0.9. This energy definitely is around 0.5. It's much smaller than 1 electron volt. And the peak which you see there is definitely higher than 0.5 electron volt. So that's why I think it's really going from your LUMA +1 to LUMA rather than not that arrow, but the arrow between LUMA +1 to LUMA. Then this energy range corresponds to your peak. Yeah, this one. So it's slightly less than 1 electron volt, but definitely higher than 0.5.
Well, I guess. Well, those are the 2 possibilities to consider. So when I look into them further, I'll see what these orbitals look like and see if it makes sense whether it luminesces from either of those transitions.
Actually, could it create this shoulder, this what we call vibronic shoulder? Can we treat it this way?
No. For vibronic shoulder, for the quantization of nuclear motion, the code is neglecting it. There is a approximate account of the what we call vibronic shoulder in slide 17 as I see it. But yeah.
Yeah, so everything here is purely electronic in terms of like the line width.
Okay, so something a little bit.
No, that was a natural idea though.
Is it the only complex which showing this strange spectra, kind of very different spectra?
I don't remember. I guess we'll have to go through. So this is 3A. These look fairly normal.
What about those complexes where you have, I think it's 5B and 5C showing this B excitational curves?
Mm-hmm.
If you just go there directly.
B. So the transient peaks seem to be a little more pronounced, but not as much.
So it's
Because they have charge transfer characters, they're not as bright.
optically inactive, probably.
Mm-hmm. Yeah, and this is from the whole too, which is different. And so 5C. Yeah, there is a fairly IR energy range feature which has about a 1 picosecond lifetime, but it has a small contribution to the overall spectra.
Okay, yeah. So I guess it's only 3C, and I would definitely recheck it once again. Maybe it's really computational error rather than actual results. Just check because it looks so suspicious.
That's what I initially thought too, because it was.
In terms of electronic structure and everything, it's not so much different comparing to the other complexes, right? I mean, like this splitting between levels are not very different. The character between these levels are not very much different. So I really don't see a good reason for explaining such a drastic difference in terms of making this intra-band transition being so optically active.
Mm-hmm.
So just take a second check for maybe occasionally you use somewhere some data were mixed up or something when you were proceeding through these calculations, or we need to find some physical reason for that. Okay.
Yeah. So yeah, that's everything I have to show.
Okay, are there any conclusions?
I guess I'm not sure how everybody else kind of views the narrative of the story yet, but at least what makes sense to me is that we shown we can tune the band gap by changing functionalizations to the desired energy range that we want for luminescence. But the groups that give the right band gap for the luminescence kind of have detrimental aspects for carrier cooling and non-radiative recombination. So it's kind of a balancing act as to how to get optimal IR emission, but then also optimal yields.
And I think we should have an open question about PDE versus PDE0 effect on the rate, on the quantum yield.
Mm-hmm. Yeah, in terms of the accuracy. Yeah.
If it's not taking too much time, probably really do it for the complex 3C or 3A, the complex which we have experimental data. Just to see how much off we will be with experimental value in the case if you take a function which provides better agreement with energies. Although actually if you compare with experimental data, right? So the emitting energy which they report is 1.94 electron volts. I already converted it. And your energy is 2.6, right? So we still 0.6. It's almost half a electron volt difference between the experimental value and the calculated one. So we kind of the PBE still overestimate this energy. So PBE 0, PBE underestimate, and PBE 0 is overestimate the energy. So that's why it probably naturally will increase the quantum yield, because energy now is blue shifted comparing to experiment, while pure GGA will underestimate. So like neither of them probably is really perfect. Plus, as I said, we don't have any salvation model here, which for sure will reduce, in any case, will reduce the quantum yields. And plus all other small imperfections which are present in the experiment, or pathways which provide loss in the quantum yield non-radiative track. Yeah, so I would say, since we already start working on this comparison between the different functionals, I would definitely finish it with the one which we can compare with experiment, just to be sure. But of course, as I said, like, we should not expect, I would say, would be really hard to say which functional is better to use in direct comparison to experiment, because as I already said, in one case we have a blue shift, in the other we have a red shift with respect to the experiment. So neither of them really is perfect. But
Okay.
in the paper, I think the main point will be for comparison of the trends. So we can really compare how this substitution affects the quantum yield of the emission, rather than just really promising 60%, 70%, and so on, right?
Right. Yeah, the yields, like comparing between the molecules, makes sense. As in terms of which functionalizations work the best.
Yeah. And again, if we have two complexes calculated with different functionals and see the trends are staying the same, although the numbers are twice bigger or wherever they're bigger, right? So then again, we have a good solid reason to make this conclusion. Like we think already pointed on it. Like, we cannot just wave by hand saying that, oh, we expect the trends would be the same, despite that the values are twice bigger.
Okay.
Yeah,
Well, yes.
okay, I have one more question. I'm just wondering, is for the emission quantum yield measurement right now, and I know it's in vacuum, does not include any solvent model. Is that due to the current code? This one certainly the calculation is using the code developed by Dimitri's by your lab, so it's not like a Gaussian. It already included in the Gaussian. So how difficult to include solvent mode in your computational code? I'm just curious.
Thank you. So it is very challenging. It is doable, but not on a short notice. So VASP software, that is our engine, doesn't include polarized continuum medium to account for solvents. But there is a additional package which is named VASP Sol, which needs to be purchased and merged into VASP to do this polarized continuum medium. So just a second, on one hand, and on another, one can always do explicit solvent, which will be an expensive calculation, but kind of more reliable. So if there is a serious reasons and available experiment, it is doable, and maybe even with high reliability. Yeah, sorry for interrupting.
But even if you go with this additional package, my understanding, it will not support the dynamics. It will be just giving you solvent.
No, it will, when any calculation along molecular dynamics and couplings will be done in presence of this solvent.
Yeah. So the same way as you calculating this PB0 functional, right? So you kind of like the change in geometry is actually not affected by the functional. It's only the electronic structure which you calculate with a functional, right?
Since electronic, so to say, clouds, electronic density is polarized by presence of the solvent, the forces will be different, and molecular dynamics can go into different direction. So it's likely the trajectories will be different, but it's hard to say without trying it. And most expensive but most reliable would be just explicit placing solvent molecules around the dye.
Okay. So I understand, yeah, you need an extra additional package and the calculation will be more expensive. So is this part of your plan in the near future? Depending.
I still not convinced 100% that this package really will work for dynamics.
It will work, but it will be
You're saying, okay,
technical problem to merge it for dynamics. So it's not there are expectations that it will work, but it's too much additional work. So it is not a short-term project.
PBE zero functional. When you do PBE zero functional calculations, you not run adiabatic dynamics with PBE zero. Am I right? You recalculate it only for the couplings when you already have your trajectory done. Adiabatic trajectory is calculated with PBE, not PBE zero with your calculations. Am I right?
Correct. This is correct. But VASP Sol is an addition. Is not a new functional. Is additional tool that affects all electronic.
To include the solvent media, you need actually to again do the same thing what they do with PBE zero functional. You need to go to the localized basis set, and this is the main threshold why you can why it's very inefficient to use the hybrid functionals for the dynamics in VASP because you need localized basis sets for that, and then it's becoming very slow. You really need to go from your plane wave basis set to the localized basis set in each moment of time, and it will be exactly the same requirement for the whatever they call it, polar media, right? Sizable media. So that's why I doubt that this will be really a solution for including the solvent. It probably will be cheaper because the molecules are not very big. It probably will be cheaper to include the solvent, like one layer of solvent, rather than try this new package.
Okay. So please join me in thanking Aaron for interesting presentation.
Thank you, Aaron.
So any additional questions? If no, the scientific part of the meeting is done. Everyone is welcome to disconnect, and I'll add a couple of words about the next meetings if anyone is interested. So Aaron, would you please stop sharing? Okay. I have 3+1 comment, or 4+3. So what we have observed today, what Aaron presented, includes the transitions between electronic states. And if you are looking onto industrial applications, then such transition between electronic states play a role in light emitting diodes, in bioimaging, in photovoltaic applications, in photo detectors, in cameras. And in order to take into account such processes, one needs to go beyond standard equilibrium electronic structure calculations. So there are additional tools to take into account how the photoexcitation drives system from equilibrium, how it promotes electron from occupied to unoccupied moiety, what you saw in Aaron's presentation. And then through interaction with lattice vibrations, it shows how the energy of excited state is dissipated into heat, into nuclear motion, and then this heat dissipation is associated with system experiencing jumps of electrons and holes between orbitals. So if you see value in such calculations, then and if your project is related to such things, then you do have a summer program in reviewing again for those who are practicing, and just bringing it to those who never practice it, the codes that you saw them working for Aaron, and it will be chopped on several knowledge transfer sessions with maybe like 4 or 5 presenters each time. So I see at least there will be a session on couplings, a session on the averaging procedure, how couplings are converted into rates, and then the session on photoluminescence, charge transfer, and quantum yield. So during the summertime, we will set 3 such sessions, and we'll agree together when to do them. Also, there will be at least one, maybe more meetings assigned for Aaron to present his practice talk before the defense. Well, it's not mandatory, but I think it is to Aaron's interests to practice it before it goes formal. And there will be several research updates and literature club. And I suggest if Kea is interested to make an update on, I see yes in the chat line. So next Tuesday, Kea, please prepare slides and be ready to answer unexpected questions for your project. So if anyone volunteers to present specific research update or journal club paper, feel free to access this document. It is open for writing, and just place your name into one of the open dates, and we will process it further to comfort of everyone. Whew. Meeting is done. Thank you much to Aaron and to everyone for joining in, and I'm really impressed by this exceedingly high attendance that we haven't seen for like at least half a year. So thank you for joining, and looking forward to see you again at this